The first power theorem is called the chord-chord power theorem, and not surprisingly, it involves two chords intersecting in a circle. And it tells us that when this happens, the product of the parts of each chord are congruent. So in other words, VE times EN will equal LE times ES. Now let's take a look at a proof as to why that's true. All right. Well, the first thing we have to do is to draw segments VL and SN to create two triangles. Now, since angle V intercepts the same angle or the same arc as angle S, these two angles are congruent. By vertical angles, I know that these two angles at E are congruent, and since angle L intercepts the same arc as angle N, those two angles are congruent. So clearly, these two triangles are similar by angle. Now, if I set up the congruency, I see that if I set up the proportion, I see that VE over SE is congruent to LE over NE. And when I multiply that out, I see that, sure enough, VE times NE equals SE times LE. I get confused a little bit by the notation of segments, so I just call the first part VE A and EN B. LE I refer to as X and ES is Y. So I remember the chord power theorem as A times B equals X times Y. Okay, let's take a look at the tangent-secant power theorem. The tangent-secant power theorem involves a tangent and a secant. And this one tells us that if a tangent is drawn to a circle from a point outside the circle, and a secant is drawn to the circle, then the square of the tangent is equal to the external part of the secant times the whole secant. So in other words, TP squared is going to equal PR times PQ. And the way we'll prove that is once again using similar triangles. If I draw TQ and TR, I'll see that triangle PRT is similar to PTQ. Can you see why? Why don't you pause the video to make sure? Hopefully you saw that both triangles shared angle P and that angle R and angle QTP are congruent since they both are 1/2 of arc QT. Therefore, the triangles are similar by angle, and I can set up this proportion. PR over PT equals PT over PQ. Multiplying that out, I get the desired result that PT squared equals PR times PQ. Okay, there's one more power theorem to look at, and that's the secant-secant power theorem. And once again, it's not hard to see where it gets its name. It's based on two secants being drawn from a point outside the circle. This time we'll see that the external part of each secant times the whole are congruent. So PA times PB equals PC times PD. Let's take a look at how they got that. Well, once again, we're going to draw some auxiliary lines, this time BC and AD, to form some similar triangles. They're similar because both triangle PBC and PDA have angle P in them, and angle B will be 1/2 of arc AC, and angle D will be 1/2 of arc AC. So those two angles will be congruent. Up there. You can barely see the tick mark. Okay, so knowing that these two triangles are congruent, PAD and PCB, we have our proportion PA to PC is equal to PD to PB. By the means extremes product theorem, we multiply those out and we have the desired result. that PA times PB equals PC times PD. All right, Ramblers, let's take a look at a couple of examples, and then we'll conclude the video. Thanks for watching. Okay, number 8 on page 496 is a really good problem because it's possible to get the right answer for the wrong reason. So it really helps us to make sure we have the correct understanding of the secant power theorem as well as the tangent secant power theorem. So let's show you how to do it right, and then I'll come back and show you the mistake that you might have made but wouldn't know it because you got the right answer. Okay, the first thing you have to do is label this chord x because we're going to need that in order to use the tangent secant power theorem. And that theorem will say that the tangent drawn from a point outside the circle to the circle squared equals the external part of the secant from that point times the whole secant. So notice that it's 6 squared equals 4 times the whole thing, 4 plus x. At this time, the 3 and the 4 aren't involved at all. So solving this for x, we see that x equals 5. Now we can use the secant-secant power theorem to solve for y. And that tells us the external part of the secant times the whole thing, which would be 3 plus y, equals the external part times the whole thing, which we've now learned to be 4 plus 5. So we solve this for y. And when we solve, we get y equals 9, which is exactly what the correct answer is. But let's see how you might have done that wrong. Okay, the wrong way looks a lot like the right way, so you got to be careful. See, the wrong way would involve what looks like the tangent secant power theorem. And you might say that this tangent, 6 squared, should equal the secant 3 times 3 plus y. If you solve that, you'd also get 9. But the problem with that is it doesn't satisfy the theorem. The theorem says that we have to draw the secant we're using and the tangent we're using from the same point outside the circle, like right here at point P. The reason this doesn't work is the secant they mention in the wrong way comes from another point. I'm going to call that point Q. And so the theorem just doesn't apply. So even though you get the same answer, it's not right. So I hope that makes some sense. Let's take a look at another problem. Okay, number 14 on page 497 is another one that gives students troubles every year. The problem is the diagram makes it look like that pipe that is suspended is a diameter. And really the diagram should look something like this. So that arch isn't half a circle, it's just part of a circle. And if we try to find the distance to the center of the circle, let's call that x. We draw a radius, and now I know that radius will be x plus 5, just as this distance here is, x plus 5. And then half of the chord, since it's bisected, is 10. So we get a right triangle that is an x, 10, and x plus 5 triangle. So we have to solve this quadratic. So when we solve that, we see that x equals 7.5, and when we plug that back in, we find that the radius is 7.5 plus 5, or 12.5. Okay, once you get past the diagram, most students do okay with that. You can also use the Chord-Chord power theorem to solve this one, but I think this is kind of the most straightforward. Okay, thanks for watching, Ramblers.